All right, so let's look at approximating square roots. And approximating square roots is what we do when we don't know a perfect square, we don't have a perfect square problem. So given these numbers here, they're perfect squares. So if I ask you what's the square root of 36, you would say 6. If I ask you for the square root of 25, you would say 5. But what if I ask you for the square root of 11, or the square root of 21, or the square root of 35? So it doesn't mean they don't have an answer because they're not on this list. The calculator will give you an answer if you plug it into a calculator. However, we want to come up with the ideas of how do we approximate these square roots? What do we look for and how do we do that? So before I do that, I want to give you some definitions of rational and irrational numbers, but I'm going to give you the definition after we've explored them so it's a little bit clearer. So we have what's called real numbers. Real numbers is a world of most numbers that you've seen on the number line or that exist with calculations in mathematics. And they come into two categories. One category is rational numbers, and another category is irrational. Now, giving you the definition of these two might not do justice unless I actually explain to you what they are and their characteristics. So, rational numbers are any number that can be written as a fraction. Okay, so if you notice, the word rational has the word ratio in there. Ratio. And remember, a ratio is a fraction. So think of that. If it's a rational number, it means you can write it as a ratio or a fraction. So some examples would look like the numbers 1, 2, 3, 4, and so forth. Okay, those are all rational because we can write this as 1 over 1, 2 over 1, 3 over 1, 4 over 1. So technically they can be written as fractions. And then we have whole numbers. These are whole numbers, counting numbers including 0. And then we have our integers, right? You have -1, -2, -3, and so forth. Okay, all of these are also rational because, again, they can be written as fractions. Every number can be divisible by 1. So you can write a 1 under all of these and you'll got your instant fraction. And, of course, fractions themselves. 1/2, -2/3, 2.25, 3 repeating. Anything that's a fraction or decimal are considerations. Now, here's the special category, which is decimals. If I give you a decimal like this, 0.27 with the bar on top, can you predict what comes next if I write it in expanded form? What's next? What's next? What's next? So, although it does go on forever, we can predict what comes next. So it's considered rational, okay? For example, if I have the number 674 bar, and I ask you, can you predict what comes next? 0.67467, and then what's next? 4. What's next? 6. So because you could predict what comes next, that's also considered rational. Again, if it's got that repetition bar. Now, a little side note. There's a trick that allows you to write these repetition bars, create numbers with repetition bars, and that's the division of 99 trick. So I quickly want to show you, just because I would hate to move on without showing you this. So if I have 5 divided by 9, that's 5 repeating. The 6 gets rounded off. If I have 6 divided by 9, it's 6 repeating. 2 divided by 9, what do you think that is? 2 repeating. If I get 4 divided by 9, what do you think that is? 4 repeating. So anytime you divide by 9, it repeats that digit. So if I have, for example, 4 over 9, that's 4 bar, which is 4 repeating. Okay. And another trick is, say I have 28, 1. that can be written as 999. And anytime you have a number divided by multiples of 9, you get repeating numbers. 128, I'm sorry, 281, 281, 281. All right, so the rule is this. If you want to write a number as a fraction, if it's got 3 digits, then you divide by 3 nines. If you want to repeat a 2-digit decimal, then you divide it by 2 nines, 99. So that one would have been the same as 27 over 99. So if you don't believe me, I'll show you. 27 repeating. All right, so this is just a little trick. This one, 674 repeating. It's got 1, 2, 3 digits. So I'd write it as 674 over 999. And 674, 674, 674. All right. So anytime you see these repetition bars, they could be written as fractions. All right. That was a side note. Moving on. Irrational numbers. Irrational numbers are numbers that are, well, irrational, crazy, don't make sense, they're confusing, they're hard to understand. So what would those look like? They would actually look like numbers that don't have a pattern. Okay, there's no repetition bar. I don't know what comes after 8. You don't know what comes after 8. We cannot predict it, so therefore it's irrational. And one of the most common ways to come up with an irrational number besides making it up is to take the square root of a number that's not a perfect square. So let's see. So let's clear this. We'll take the square root of 7. And you get this. Now if you look at this number here, there is not a pattern. 645751311064591. I don't know what comes after that 1. And if you believe it or not, this can take up an entire computer screen and never have a repeating pattern of any kind. So that is an irrational number. Same thing goes with any other irrational number. Okay, so anytime you have the square root of a number that's not a perfect square, you'll get an irrational number. So just show you 11 square root, long crazy number that goes on forever without a pattern, and 3 square root, another number that goes on forever without any patterns, and 41 square root, another long number without a pattern. So these are the way you come up with an irrational number. Right, so let's look at example 1. Rational or irrational? All right, so here's a series of numbers. We're going to analyze them. So let's look at the first one. Is that rational or irrational? Remember, rational is simple, easy to understand, predictable, and it can be written as a fraction. Irrational means it's got no pattern, there's no way of predicting the next decimal in line, and it is irrational. So in this case, if I ask you what comes next after 1, you would say 2. And then next, and then you say 1, and then you say 2, and then 1. So therefore, this can be written as 0.12 with the repetition bar. And from there's a trick that I know that because I have 2 digits repeating, all you do is you take those same 2 digits and each digit needs a 9. So 12 over 99. And if you don't believe me, I'll show you that 12 divided by 99 is 12 repeating. Okay. So therefore, I was able to write this repeating decimal as a fraction, so I know for sure that's a ratio. Rational. And 7 over 11, that's already a fraction in itself. So of course it's going to be rational. Square root of 12. Is there a number that exists that is multiplied by itself gives you 12? Can you create a square with 12? As a whole number, no. But there is an answer, and it's a decimal. So let's look it up. 12, square root, there's the number. Do you see a pattern here? Can I put a repetition bar on this number? Do you know what comes after 5? I don't. So therefore, this is irrational. Square root of a non-perfect square is irrational. I for irrational. And D. How about this one? 0.32 repeating. I do know my 9 trick. I take the 2 digits that are repeating and I divide each one of them by a 9. And I can show you that 32 divided by 99 is 32 repeating. So because I was able to write it as a fraction, I will definitely say it's rational. All right. Now the easiest way to come up with your own irrational number is to create the square root of a number that's not a perfect square. All right. So let's get into predicting what these values are. Notice I was using my calculator to get those square roots, but I'm going to show you how you can do this without a calculator. So first we need to recall our perfect squares. And if you don't have them, it's good to have a list handy when you're doing these problems. The perfect squares are 4. I can make a square by, it's 3 by 3. 4 by 4 would be 16 squares. 5 by 5 would be 25 squares. A 6 by 6 would be 36 squares. And 49, 64, 81, and 100. Now, these perfect squares I got to recall. The square root of all of these. Square root answers would have been 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. And what I mean by that is the dimensions. 2 by 2, a 3 by 3, 4 by 4, and so forth. All right, so now estimate this example 2. Estimate the square roots. Okay, so for example A, I want to find the square root of, let's say, 7. All right, so to estimate the square root of 7, we want to think about where it lies as far as our perfect squares that we do know. So we do know that the square root of 4 is 2, and the square root of 9 is 3. But the square root of 7 would lie somewhere between those two. So we're going to write down the perfect squares that we have before 7, which would have been the square root of 4, and a perfect square after 7, which would have been 9. So because I know that the square root of 7 lies somewhere between 4 and 9, and I do know that the answer to this one is 2, the answer to this one is 3, so therefore the answer to square root of 7 would be somewhere between 2 and 3. Now we also want to keep in mind that halfway in between 4 and 9. So I'm just going to write some numbers down. So I have the numbers 4, 5, 6, 7, 8, 9. 4 is already this one here. 9 would be this one here. And 7 is here. Now is 7 right in the middle between 4 and 9? It's not, right? It's a little bit to the right. So 6.5 would have been perfectly in the middle. So I'm going to say it can't be 2.5. It cannot be right in between. It's going to be a little bit closer to the 9. So I'm going to say 2.6. All right. So the idea is this. You have 7, and you know it's between 4 and 9. Why are we using 4 and 9? Because we do know that 4 is a perfect square that comes out as a whole number 2. 9 is a perfect square that has a whole number answer of 3. So 7, since it's in between, must be some number between 2 and 3. I could say 2.5, but that would be assuming that it's perfectly in between 4 and 9, right in the middle. And it's not, so I listed the numbers from 4 to 9. And I saw that 7 was not right in the middle. It was a little bit to the right, closer to 9 than it was to 5. What number would have been right in the middle? 6.5 would have been right in the middle. So therefore, I do know that 2.5 would not be the best estimate. So I just went one closer to the, 1/10 closer to the 9, or closer to the 3, and I got 2.6. Okay, so let me do that strategy again with another number. Let's try the square root of 12. We did that one earlier on the calculator, but this time we want to do it ourselves, estimating. So what square root is a perfect square before 12 and after 12? So square root before 12 would have been 9. And the square root of perfect square after 12 would have been 16. Now I know that this has an answer of 3. And this one has an answer of 4. So what would the answer of 12 be? Now, let's see. Is 12 closer to the 16? Which means I'd have to go closer to the 4. Or is 12 closer to 9? So my answer should be closer to 3. So let's find out. I'm going to write down again all the numbers. 9, 10, 11, 12, 13, 14, 15, and 16. 9 was the one I started with. 16 is my ending number. And I have this one right here, 12. Is 12 right in between 9 and 16? 12.5, right? 12.5 would have been right in the middle. So that's what 3.5 would have been. Perfectly between 3 and 4 would have been 3.5 if I had 12.5 right here. So since 12 is not right in the middle, I do see that it's a little closer to the 9 than it is to the 16, which means the answer is going to be closer to the 3 instead of being closer to the 4. So I'm going to start at 3.5, but then I'm going to tell myself it can't be 3.5. I'm going to go a little closer to the 3 and say 3.4. Okay, so that's how you estimate. You try to think of the halfway point and then tell yourself, is it closer to the 9 or closer to the 16, and then make your estimate. And this is an approximation because we're estimating. All right, so let me use my calculator just to kind of double check and see what we get. And I see that the square root of 7 is 2.64, and I said about 2.6. And over here, square root of 12, 3.46, and it rounds off to 5, but close enough. If you're off by 100th or a 10th, then we know you're thinking right. All right, let's add an extension to example 2. We'll call this C and D. Find the estimate to the square root of 24 and estimate the square root of 17. All right, so the square root of 24, perfect square before 24 is 16. And again, you can reference your list. And I know that the perfect square after 24 is 25. I know that this answer is 4, and this answer is 5. So this number is going to lie somewhere between these two. Now it's going to come to the point where listing all these numbers is going to be a headache because they're going to be spaced apart enough to where you're not going to want to write them all down. So right now I'll do it quickly, but try not to use this strategy, but we'll do it now. 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. I got 25, I got 16, and my 24 is right here. So 24 is right before 25. If this one has an answer of 4, the answer to 25 is 5. I'm not going to be in between these two and say, oh, 4.5. Because that would have been somewhere right here in the middle, like the square root of 21 or something. 1, 2, 3, 4. Yeah. So 20.5 would have been 4.5. I'm nowhere near the center. I'm way over here close to 5. So square root of 24, I'm just going to go ahead and say 4.9. Close enough to almost being 5. All right. Next one. I got 16 is the square root before 17. And then I got the square root of 25 after 17. All right, so we got the same set of numbers, right, between 16 and 25. But this time, I'm going to use the same row here. Well, let me just write it over. So I got 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So I got 16 already, 25, and this time my 17 is right here. So instead, I know this one's 4. I know this answer is 5. 4.5 would have been right in between 4 and 5, which means my square root would have been like 20.5. So I'm not even close to getting close to the center. I'm like only 1 away from 4. So I'm not going to use 4 because that's the answer for 16. So instead, for 17, since it's just the next square root over, I'm going to say 4.1 as my estimate. All right, and remember these are estimates. So let me just quickly verify that for you. Square root of 24. 4.89, which is close enough to 4.9, and square root of 17 is 4.12 something, so close enough. All right, so there you go. Let's just do one more because I don't want to have to write the list down, and see if you can get a close estimate, and then we'll be done. So I'll just make this a bonus. Estimate the square root of, let's make this one 52. Think about it. All right, we should have put here square root of 49 is before 52, and the square root of 64 is after 52. 49, the answer to that one is 7. And the answer to 64 is 8. Now 52, is it closer to 8 or closer to 7? 7 point what? That's the question. Well, 49, 50, 51, 52. So there's only a difference of 3 digits here. Then from 52 to 64, that's 12-digit difference. So clearly, we got 12 digits away from here. It's not going to be close to 8. And then we got only 3 digits away from 49. So I'm thinking closer to 49, like 7.2 maybe. It's clearly not halfway in between. It's closer to the 49 number, so it's closer to the 7. Using 7.5 as my middle marker. So let's just verify that. 52 square root 7.211. So there you go. And again, if you're off by a tenth, as long as you know that you're either before 7.5 or after 7.5, that prediction means that you know what you're doing. There you go.